everyone, Daniel here for Rock the JVM, and this video is a short but end-to-end tutorial on Kafka Streams for Scala. This is an exciting topic that's been requested quite a lot on the Rock the JVM channel. So here in this video, I'm going to assume that you know some obvious Scala fundamentals. We're probably going to use a bunch of implicits in this video as well. And in order to run Kafka, we are going to need Docker installed on your computer. So here, if you want to install Docker, you can go to docker.com. The link is called docker.com/product/docker-desktop, and this will be the link to the Docker desktop application. You can install it on your computer. It's completely free, and it allows you to run Docker containers on your platform. Good. So after you've installed Docker Desktop, you can pause the video, obviously, if you need more time to install it on your computer. The recommendations are, as always, just write code with me, and you'll get an end-to-end workflow into Kafka Streams. And whenever you need to refresh your memory, just refer back to this video or to the written form at the blog with the link in the description. And this is one of the few times where I actually recommend you have the article in front of you, because we are going to use a bunch of already made code. So in order to not type it yourself, I recommend that you copy these snippets and add them to your project, in particular the Docker Compose YML configuration for Kafka. So this green code is pretty much everything that you'll need to run Kafka as a Docker container. So I recommend that you select everything and copy and paste that into a Docker Compose YML file and bring it into IntelliJ IDEA or wherever you want to store that. In my IntelliJ IDEA, I have a Kafka Streams object with a main method because we're going to test this live. And here under a folder that I've set up in my own project, I have a Kafka folder where I stored Docker Compose YML, which contains the exact code that you can find on the blog post. Now, after you've stored the Docker Compose YML, I would like you to navigate to the folder where you stored the Docker Compose YML file. So I want you to right-click and copy its path. So I'm going to copy its absolute path, and then I'm going to open a terminal and I'm going to navigate there. And then I'm going to do docker-compose up to start up my Docker containers. Now, if this is the first time you're doing it, Docker Compose up will take a few minutes to bring up the appropriate images and start the appropriate Docker containers. If you have done this before with the exact same Docker containers, this is probably going to go much smoother and much quicker. So here you can pause the video if it takes a little longer to start up your Docker containers. And here you will have a Kafka broker and a Zookeeper already set up for you. Alright, so you can pause the video and set up your Kafka Docker container to test whatever we're going to write in the rest of this video. Additionally, we are going to need some libraries for our IntelliJ project in Scala, so you can go at the top of the blog post and you can copy the library dependencies code and add them to your build.sbt file. I already have them in my own build.sbt. I have a bunch of libraries here, but what we are going to need is Kafka, Kafka Streams, Kafka Clients, and Kafka Streams Scala. These are the libraries that we're going to need in order to interact with our Kafka entities there, and Circe in order to serialize our data structures to JSON and send them to Kafka. Alright, so that being said, I'm going to move back to my Kafka Streams application and I'm going to start showing you the actual tutorial. So the example that we're going to work with is the updating of orders, discounts, and payments in an online store. So assuming you have this giant online store where people buy stuff from you, and there are millions of people potentially purchasing things from your online store, and you want to keep track of the events from your online store. So I'm going to set up a small object that I'm going to call domain, and I'm going to simplify this use case quite a lot. I'm going to write a type, let's call this user ID as string, just to use the appropriate type aliasing for our business use case. And for your particular example, these might actually be case classes with additional data, but I'm going to keep things simple. I'm going to say profile as string. I'm going to define another type. I'm going to call this product which is again a string. It might be a case class in real life. I'm going to have a type, let's call this order ID, which might be a unique identifier. I'm still going to store that as a string. And I'm going to define a bunch of case classes for the actual data that I care about for my little online store. For example, I want to care about an order. So an order will have an order ID as an order ID, a user as a user ID, and products for whatever baskets the user might want to purchase. So I'm going to have a list of product. And let's say an amount, which is the total price of the entire checkout basket. And I'm going to store that as a double, but never ever use double for money. So I'm going to actually say that out loud. So never use double for money. This might get you into real trouble. And I'm going to have a case class. I'm going to call this discount, assuming you might want to offer promotions for some of your products. So I'm going to have a profile as offering a discount to a particular user profile on your application. And let's say amount, which is a double. So you might want to give people, let's say a $10 off or a $100 off for a particular promotion. And I have a case class. I'm going to call this payment that you want to keep track of inside your online store. I'm going to have an order ID, and I'm going to have, for example, status, which is a string. So I want to actually have that as a type alias. I'm going to call this status as a string. You might use either one. So I'm going to have that as a status. Cool, so this is our little domain for our little online store. And if you know Kafka, you know that you can send messages into a broker that has a special concept known as a topic. So you can send a message through a topic and you can have many, many subscribers onto that topic, and everybody will see the message that you send through that. So I'm going to have an object, I'm going to call this topics, and I'm going to define a bunch of strings that we are going to use as topic names. So I'm going to have a val, I'm going to call this orders by user as orders by user. I'm going to call another val, let's call this discount profiles by user, and I'm going to have that as discount profiles by user, and a bunch of others. So if you want, you can use them from the blog post and paste them into your application if you want. I'm going to type them myself so that I don't mess up anything. So I'm going to have discounts. Let's call this discounts. I'm going to have another val. Let's call this orders as orders. I'm going to have another val. Let's call this payments as payments. And let's say paid orders. So just those orders that have been paid for. So paid orders. All right. Now we need to create these topics into Kafka, but the commands to create Kafka topics are quite tedious, and typing them manually is a bit of a burden. This will take 10 minutes just to type them. So I'm going to generate them automatically. So I'm going to run an IntelliJ trick. I'm going to hit Option twice and then hold them, and then hold Shift, and then I'm going to select multiple strings here, and then I'm going to select everything, and I'm going to create a list containing all of these strings, and then I'm going to hit Option twice. This might be Alt on Windows, and then have a multi-cursor and have some commas here, and then I'm going to have a for each, and then considering every topic, I'm going to print line the Kafka command. So I'm going to have Kafka-topics, and then I'm going to have -- bootstrap server. This is going to be localhost 9092. This is going to be the URL of my Docker container. And then I'm going to have -- topic, and then I'm going to insert topic here. And I'm going to have -- create. So this will be the commands for all the Kafka topics. I'm going to run this, and I'm going to basically print out all the Kafka commands. assuming the code compiles in a reasonable amount of time. I have quite a bunch of Scala code, probably holding 70% of the Rock the JVM channel. So these are all the Kafka commands that I'm going to use. So here, into another terminal, while the Kafka dockers are still running, I'm going to say docker exec -it broker bash. So this will open a bash terminal inside the broker docker container, which will hold all the Kafka commands. And this will create a little prompter. And then I'm going to paste all my Kafka commands. So I'm going to paste that, and this will take care to create all these topics for me. So as you can see, even creating a topic takes a little bit of time. Even typing them manually would have taken a little bit longer. And now we have all the topics for our little fictitious online store. So we now have all the topics. All right, amazing. So the utility of Scala is pretty apparent now. Cool, amazing. So I'm going to remove the program that will just output all the Kafka commands, and then we need to get back to our Kafka tutorial. All right, so the Kafka Streams library is a client library in the sense that it manages streams of messages that you can send to Kafka. So Kafka is an independent entity, and you, the writer of this program, is a client of Kafka. And Kafka Streams are composed of three primary entities. One is called source. So a source is the emitter of elements. So a source emits elements of a particular type. And you have flows, which transform elements along the way. So a flow is a transformer, so it transforms elements along the way. You can think of map, for example, is a transformer. And we have a sink, and sink is where messages are consumed. So after a sink, they don't exist anymore. So a sink will just ingest elements. All right, now in Kafka Streams, sources, flows, and sinks are called stream processors. And a streaming application is just a composition of these sort of elements. Now, in order to be able to have our data processed by these elements of Kafka Streams, we need to be able to serialize and deserialize our data structures to and from a string. So we are going to use Circe to serialize these strings as JSONs. And to that end, I'm going to import a bunch of Circe packages. So I'm going to have io Circe generic auto, which is the macro capability of Circe to generate encoders and decoders. I'm going to import io Circe parser, and then I'm going to also import io Circe syntax, which is a package that contains extension methods. And then I'm going to import encoder and decoder, but IntelliJ will be smart enough to import those automatically. Now, the way that we are going to make our data structures compatible with Kafka Streams is to be able to serialize and deserialize them to arrays of bytes that Kafka can then handle. And we're using Circe to turn our data structures to JSON strings and then turn that into bytes. So here's how I'm going to do that as an example for, let's say, an order. An order is a case class, and case classes are automatically serializable to JSON through this import, which is based on macros, and Circe is able to automatically create encoders and decoders for case classes automatically. So here's how I'm going to do that. I'm going to say an implicit val. So implicit val, I'm going to call this surde order, which is of type surde, of type order, and I'm going to import my domain object. So I'm going to import domain everything, and surde is a data structure that is based on Apache Kafka. So I'm going to import that from org Apache Kafka, and I'm going to create two functions that are able to, one, serialize an order to an array of bytes, and second, deserialize an array of bytes into an order. So I'm going to call this serializer, and I'm going to run that as a simple function. So let's call this order of type order. And I'm going to turn that into an array of bytes as order dot as JSON, which is available as an extension method through the imports that I've added. And then I'm going to say .nospaces.getBytes, which is an array of byte. So this is how we can turn an order into an array of bytes. And now we need a deserializer to do the reverse. So I'm going to have a deserializer as, I'm going to call this bytes as array of byte. And then I need to return a order. But obviously the deserialization might fail. And so in order to make this function work well, we need to return an option of order rather than an order directly. So I'm going to run a bunch of operations to turn this array of byte into an order. So I'm going to call this, let's call this string as new string based on these bytes. And then I'm going to run a decode function on this string based on Circe to obtain my data structure. So I'm going to call this maybe order. Let's call this decode with the type order. So decode is a function available in Circe. And then I need to pass as argument my little string, which I've just created. So this maybe order is an either which contains an error or an order, and I need to turn that into an option. So I can say toOption, and if you want to handle the parsing error yourself, you can also do pattern matching, as you can see in the blog post, for example. So in the blog post, we have the freedom to write a little bit more code to handle the order manually, but I'm merely turning this either into an option. And so I'm going to return this value as the result of the function, which takes an array of bytes and returns an option of order. And now I need to return a Circe data structure for Kafka. So I'm going to use Circes, plural, and I'm going to import Circes from Org Apache Kafka Streams Scala Serialization. So Circes dot from function, and I need to run the type argument with order here. And I need to turn as arguments, I need to use my serializer and deserializer functions. So I'm going to say serializer, and deserializer. So now I have a Circe of order that I can use, or that Kafka can use implicitly to automatically convert an order to and from an array of bytes. So when we send an order through a Kafka topic, it's automatically serialized to an array of bytes. And whenever we want to read an order from a topic, the deserialization will take care of itself automatically. Now we can extend that. We can extend this code to all of our case classes by, instead of using an implicit val, we can use an implicit def. And an implicit def will take as an argument, as a type argument rather, I'm going to use a type argument A for which Circe can find an encoder and a decoder. And for case classes, that is always the case. So I'm going to use A for a context-bound decoder, which is from IO Circe, and also an encoder. So the encoder is importable from IO Circe. So this is to say that there is an implicit decoder and encoder available in scope, and these can be generated automatically by Circe through macros from this import, IO Circe generic auto. All right. So for all case classes, this decoder and encoder will always be present. And we are going to return a Circe of, instead of order, we're going to return the type argument A. And the serializer will take an element of type A. And I'm going to rename that, instead of order, I'm going to call this A. And I'm going to say decode of type A. And Circe from function will take the same type argument A. And we should be good to go. Now we need to fix a compiler error, which is to say that the type A does not conform to lower bound null. So Kafka cannot serialize and deserialize null. So we are going to run a lower bound on null here. And if we enforce the type restriction here, we can automatically create a Circe of the appropriate type. And instead of Circe order, I'm actually going to call this Circe, and the name isn't really that important because Kafka will pick that up automatically. All right, so far what we've managed to do is create serializers and deserializers for all of our data structures that we want to support for our little use case. All right, let's move on. All right, now, in order to create a Kafka stream, we need to define what is called a topology, which will describe how the data flows through the Kafka stream. And it has a declarative API with Kafka Stream DSL. And in order to do that, we will need a special variable that I'm going to call builder as a new stream builder. A stream builder is a Kafka Streams stateful data structure that will allow us to add Kafka Streams components to this topology. And at the end, we're going to simply say builder.build, which will return a final topology that we are going to build in between these two lines. So in between line 49 and line 53 on the screen right now, we are going to add new Kafka Streams components and then combine them together with some APIs that I'm going to show you. And the fundamental Kafka Streams, let's call this streaming basic component, is a K-stream. And a K-stream describes a linear flow of elements from a Kafka topic. So for example, I can say, define a value called users orders stream, which is a K-stream that I'm going to import. So I'm going to import K-stream from the Scala DSL package. And the K-stream has two type arguments, the key of each record. So I'm going to have user ID, for example. And I'm going to actually add, instead of importing all of these manually, I'm going to import the entire domain. So I'm going to have an import for domain everything. And I'm going to also import topics everything. Cool. So we have a K-stream whose keys are user IDs, and the elements are, for example, orders. And we can say builder.stream, and notice that the stream method is has a bunch of overloads, and the method or the overload that's of interest to us is the stream method that takes the appropriate type arguments and one topic. So I'm going to say stream with, let's say, orders by user. Now, we need to also help the compiler by passing the appropriate type arguments. I'm going to have user ID and order here for the stream method. And notice that we only have one error that is caused by implicits. So we need an implicit, which is of type consumed with a key user ID and order. Now, what's a consumed? It's a legacy Java way of providing a SERDI that we defined earlier for the keys and values to be able to be serialized and deserialized. And we already have an implicit def, which has the capability of creating a SERDI for everything that we have, including user IDs and orders. And all we need to do is add an import, and I'm going to have org Apache Kafka Streams Scala, and then we have implicit conversions everything. This will be able to convert a SERDI that we have already created implicitly to a so-called consumed data type that is to offer compatibility with Java as well. So this is the kind of import that we need in order to get rid of that implicit error. All right, so here we've just defined a K-stream. A K-stream is a simple linear Kafka stream of elements of type order identified by a user ID. Now, once we defined a K-stream, we can transform the elements inside in a variety of ways. So we can say users order stream, and then if we say dot, we have a bunch of transformations that we can apply to the elements from this Kafka stream. Now, I'm going to show you the fundamental elements that we can add, and then we're going to combine some of these elements together to obtain a meaningful Kafka stream. The second fundamental operator, or stream, that we can add to a topology is a K-table. A K-table is analogous to a Kafka stream, except the elements that quote-unquote flow through the stream are a little bit more static in the sense that they are kept inside the topic using a time-to-live policy, and they are corresponding to a topic that we call compacted. Compacted means exactly what I've described in the sense that elements that flow through that topic are maintained inside the broker. So I'm going to define a val. Let's call this user profiles table as a K-table that I need to import. So a KTable with user ID and profile, for example. So I'm going to store a table of profiles that are being kept inside the topic. And I'm going to say builder.table of type user ID, profile, and I need to specify the appropriate topic. So I'm going to say, for example, discount profiles by user, the topic. So this is the string, which is discount profiles by user. Now the problem is that we need to specify the cleanup policy to be compact. So in my terminal, I'm going to remove this topic and add it again using a cleanup policy to be compact. So I'm going to say we have discount profiles by user. So I just navigated to my old command here. So I'm going to say -- delete here. So I'm going to delete this topic, and then I'm going to add it back. So I'm going to have create, and I'm going to say -- config with cleanup.policy to be equal to compact. So I'm going to recreate this topic. All right. So I'm going to recreate the topic using this cleanup policy. If you try to recreate it onto an existing topic, the command will fail. All right, so that's why we needed to remove that. So this will be a KTable. Now, a KTable has pretty much the same methods as a KStream, except you also can interrogate this table using a structured DSL. So this will be a KTable. I'm going to show you an example of how to combine streams with tables and so on together. All right, now I'm going to create a variant of a KTable, which is called a global KTable. Now, what's the difference between a KTable and a global KTable? Well, a KTable, if you probably know the Kafka fundamentals, each topic has partitions. And a KTable, as well as a KStream, is distributed between the nodes in the Kafka cluster. Now, a global KTable is not distributed, but rather copied to all the nodes in the cluster. So this is copied to all the nodes, whereas, not nodes, but nodes with a D, whereas a KTable is distributed. So a global KTable, as best practice, should store few values because otherwise you risk crashing the nodes of your Kafka cluster. So a global KTable is useful for performance purposes. For example, if you want to join a global KTable with a KTable, because this one is available in the memory of all the nodes in the cluster, the join will be quite fast. Rather than joining two KTables together and sending the data back and forth between the nodes, that's called a shuffle, which is a very similar concept with the Spark shuffle, which, as you probably know, this is a very expensive operation. All right, so a global KTable is useful as long as you store few values inside. So here's what I'm going to do. I'm going to define a global KTable, and I'm going to say, let's call this discount profiles GTable as a global KTable with, let's say, user or profile and discount, for example. Let's say you're offering few discounts per profile, so I'm going to store those in a global KTable. So I'm going to say builder.global KTable or global table with the appropriate type arguments. So I'm going to say profile and discount. And then I'm going to pass my discounts topic inside. Now, this has the same requirement as a KTable, meaning that the topic needs to be compacted. And so I'm going to navigate back into my old commands here. So I'm going to have discounts, and I'm going to remove that. So I'm going to say delete, and then I'm going to add it back. So I'm going to have create, and then I'm going to say -- config, and then I'm going to say cleanup.policy is compact. And this added it back. All right, cool. So now we have a stream, a KTable, and a global KTable. Now, let's put these to better use by combining these together. For example, transforming the user's order stream and filter those that have, let's say, orders bigger than $1,000 in total amount. So I'm going to say, let's call this expensive orders as users order stream dot filter. Notice that we have functional programming primitives here. So I'm going to have filter with a tuple. So each record is identified by a key. So I'm going to say user ID and order. And obviously we can use our data structures because these are typed. So I'm going to say, for example, order.amount is bigger than $1,000. So this is how you can do narrow transformations between K-streams. So this will be another K-stream as a K-stream transformation. So every value is mapped to this function. You can, for example, map just the values. So you can say val, let's call this lists of products as users order stream dot map. So notice that you have a map which takes a 2-argument function, or you can use a specialization of map, for example, map values, where you don't really need to process the identifier of the record, you just need to process the actual value that you care about. And for example, you can say an order, and then you can say order dot products. And this will be a K-stream identified by the same user ID, but every order was transformed into its list of products. All right, so you can use functional programming primitives in this way. So you have filter, map values, and I'm going to show you a flat map version. So for example, let's assume that we want to issue the products one by one through this stream and process them individually. We can say products stream as users order stream dot flat map values, and analogous to map values, we also have flat map values, and I can say underscore dot products, for example, and this will be an individual stream of products identified by the same user ID. All right, so we have map values. You can also have flat map and flat map values, and so on. And these are some examples, all right? And they are quite analogous to regular collection processing, which is really cool because Kafka streams are operating on distributed systems. Now, some really interesting operations that you can do between streams, tables, and KTables is, for example, you can join a stream with a table, which is really, really powerful. So let's demonstrate a join. Now let's assume I'm interested in learning which orders or how many orders have been placed by people with profiles on my online store, because you can also order with or without a profile. So for example, I can say, let's call this orders with user profiles as users order stream dot join, and I'm going to say a join with the user profiles table, and you need a join operation. So I'm going to have a 2-argument lambda. So I'm going to say, for example, the order and the profile. Now, the join operation will return those records for which the same identifier was encountered. So the user's order stream contains orders identified by a user ID, and the user profiles table returns profiles identified by a user ID. So this is basically selecting from 2 entities with the same user IDs. And for the same user ID, I'm going to return a pair of order and profile. So for every pair of order and profile, I need to return the final value that I'm going to return in the returned record. So I'm going to return the tuple, so order and profile. Now there are many versions of this join operation. For example, you can also join on a custom key for every record. So I'm going to have, for example, if I'm interested in determining which orders came from profiles that have discounts. So if you remember, a discount was applied on a profile. So if I want to know if I should apply a particular amount of discount to a particular order, first of all, I need to join the stream of orders with the table of profiles, and then joining with the global table of discounts to find out if I should apply some sort of discount to those orders. So for example, I can say, let's call this val discounted orders stream. So I'm going to have discounted orders stream as orders with user profiles dot join, and I'm going to join with the discount profiles gtable. So I'm going to join this stream of orders which already have profiles, and I'm going to join that with the global table of discounts per profile. Now, I need to pass two function arguments. First of all, the key under which I'm going to offer a join. So I'm going to have, and the key will be picked from the first stream. So I need to return the profile of this record. Now, notice that each record is identified by a user ID and the value contains a tuple of order and profile. I only need to return the profile because that's going to be the key by which I'm going to select things from the global table. So just to make things clear, I'm going to write a partial function here. So I'm going to deconstruct the record which contains the user ID, the order, and the profile. So this is going to be the record of the first stream, and then I just need to return the profile. That is going to be the key by which I'm going to search in the gtable. And then I'm going to return the value of the matched records. So I'm going to have another partial function, and in case I get in the first stream, I'm going to have an order and a profile. And then in the second case, I'm going to have a discount, which is the type of the gtable. And I'm going to return an order, and I'm going to have an order.copy, and I'm going to copy the amount to be the initial order amount minus the discount. So this is selecting the key of the join, which is picked from the left stream. In our case, users with orders with user profiles. And the second function determines the values of the matched records. So finally, we are going to have a stream identified by a user ID, and we are going to obtain orders at the very end. So this is going to be identified by a user ID and an order. So the key of the elements or of the records in the return stream are going to be identified by the same type of the first stream, and the values are going to be processed by this function from the matched records. So I hope that makes sense. Cool. Now, one other interesting operation that we can do with these streams is to pick another identifier. So change the type of the unique identifier of these records. So for example, I can say orders stream as discounted order stream dot, and I can use a function called select key that takes a record in the form of a tuple user ID order. So I'm going to have the user ID and order. And for example, I want to index these or identify these by the order ID, not by the user ID. So I'm going to say order.order ID. And now this will be a stream identified by an order ID, not by a user ID, which will then allow me to join with some other tables or with some other streams as I see fit. So for example, in our case, we have a stream of orders for which we have discounts. Let's say that we want to figure out which of these were actually paid. And we have a bunch of topics here. We have payments and paid orders. Let's play around with these things a little bit. So I'm going to define a val, let's call this payments stream, as builder.stream with order ID and payment from the topic of payments. So this will be another stream. Now, a super interesting feature of Kafka Streams is that we can join two streams at the same time. Notice that the previous joins were a join between a stream and a table. So we're joining something dynamic with something static. Now, in this case, I want to join two dynamic streams. So we can join a stream with a stream under certain conditions. For example, we need a join window in between which Kafka can actually do the matching in between these two streams, because otherwise, if a record arrives too late, then it will be discarded. Otherwise, the Kafka join internal state will grow indefinitely, which we don't really want. So we need to define a join window, and I'm going to say join windows dot of, and this will take a Java duration as an argument, and I'm going to say duration from Java time. I'm going to say duration.of, and I'm going to say, for example, 5 minutes. I'm going to say 5, and we need a temporal unit. I hate the Java time APIs. I'm going to have chrono unit dot minutes. In the reasonable assumption that once an order was issued, it was also paid. All right. So we will simply set up this 5-minute join window. Now we need to say, let's call this orders paid as orders stream dot join, and I'm going to use my payment stream, and I'm going to join by this order ID. So this will be a key stream identified by an order ID. The payment stream is also identified by the order ID, so the key is already selected. Now we need to specify what happens to the matched records. So I need to have a 2-argument function that takes an order and the payment, and I need to return something if an order has been paid. So an order and payment are going to be the tuple of a particular order ID. So this is going to be the details of the order, and this is going to be the payment details of that particular order. So the matching has already been made by the order ID, and here is the detail for the order, and here's the detail for the payment ID. Now, I'm going to actually take this out because this will make the code quite cumbersome. So I'm going to have, let's call this join orders payments as order of type order and payment of type payment. And I'm going to say if the payment dot status is equal to my desired value, let's say paid or complete or something like that, I want to keep the order, otherwise I'm going to return null or something like that. But I would like to write a little bit more pure functional programming, so I'm going to wrap these in options. I'm going to say option with the order, otherwise I'm going to return an option empty. So I'm going to have option.empty of type order. So basically I'm going to simply keep the orders that were paid, right? So we have an option order, otherwise option empty of that particular type. Right, so this decides what happens to a matched record, right? So I'm going to have join orders payments, and then as a second argument, I need to pass my join window. So I'm going to have join window. So this is analogous to the first join that we had earlier, join under the table and the function that simply decides what we're going to do with the matched records. But here we both decide what we're going to do with the matched records, and we specify a join window because we're joining two streams together, not a stream with a static table. All right. So this is going to be a key stream of order ID and option order. So for every order ID, I'm going to return that particular order if it was paid. Otherwise, I'm going to return an empty option if it was not paid. Now, I would like to filter out those that were not paid. So I'm going to say filter, and I'm going to have a 2-arg function, order ID and maybe order. And I'm going to return maybe order dot is defined. Right, so non-empty or something like that. You can use whichever because this is an option. All right, so this will now be a key stream and option order. Now, I would like to be able to simply obtain a key stream where the identifier is order ID and just the order, not the option order. So instead of using a filter, I'm going to use a flat map. So I'm going to have flat map values, and from maybe order, I'm going to return maybe order dot to list or to iterable or something like that to flatten all these collections together. Now, as a final thing that we can do with the elements in a key stream, we can shove that data through a sink. So we can say orders paid dot for each, and you can run an action, maybe a simple lambda, or you can send that data through a Kafka topic. So I'm going to say paid orders or orders paid. So we have orders paid dot to, and then you can send that data to paid orders, which is the topic that we created earlier. So we're doing a bunch of processing here with the Kafka Streams, and the resulting data we're shoving through a final topic that we can then subscribe in another place in our distributed application. And finally, we're going to call builder.build. Right, so I'm going to wrap everything in main. So I'm going to have my main here, and I'm going to start the topology. And the builder.build is an operation that returns what we call a topology. After we've added pretty much everything that we needed in the builder, when we call builder.build, we are going to return a topology. Good. All right. Now, how do we start an actual Kafka Streams application? We need a bunch of properties. So I'm going to have create a props. I'm going to have new properties, which is a properties map from Java util. And then I'm going to set up a bunch of small configurations. So I'm going to have props.put. And then I'm going to say streams config from Kafka Streams, and there are a bunch of constants that we can set, a bunch of configurations. Now I need an application ID config. I'm going to call this orders application. I'm going to copy this, and I'm going to change the configuration name. So we have bootstrap servers config, and I'm going to have localhost 9092 so that I know where to connect to. And I'm going to have another important configuration, which is the default key Circe class config. All right, and I'm going to have Circe.string_Circe.getClass. So this is a bunch of reflection-based boilerplate, but we need to do this. Then we have the topology, and then I'm going to, in main, print line topology.describe so that I can see every single detail about our Kafka Streams in a less than perfect intelligible string. So let me compile this code and let's see if we actually have something working, and we don't. And that is because overloaded method negative with alternatives. That is because this math operation doesn't work correctly. Order amount minus discount dot amount. And I think we should be good to go now. You can also use discounts as percentages and obviously do the appropriate math. And at this point, our code compiles. Let's run this and let's see our little Kafka Streams topology. So notice every single connection between all the components of our Kafka Streams. This is quite hard to read. We have a open source tool that I forget the name of. I think it's called Kafka Stream Viz or something like that. You can check it out. You can also check out the visual representation on the blog for the topology that we've just created here for a more pleasing version of this graph. All right, cool. So instead of describe, I'm actually going to start the actual Kafka Stream application. So I'm going to have, let's call this application as new Kafka Streams with topology and props. Now I need to import Kafka Streams, which happens to bear the same name as my application, which is quite unfortunate. And I'm going to have application.start. So this will start my actual Kafka Streams application. As I start shoving some data into these topics, I should see some data on the other side. All right, now what's on the other side? I'm going to show you. All right, so I'm going to start this application. And in the meantime, I took the liberty of creating some console producers for every one of the topics that we're going to interact with. I'm going to describe in detail what I'm about to do. So here first, we have a console producer on the topic of discounts for every profile. And I'm going to take the liberty of pasting a bunch of code or a bunch of values here so that I don't have to type them myself. So I'm going to paste these 3 lines. So I'm having profile 1 with profile and amount 10, which is $10 for a profile named profile 1, $100 for profile 2, and $40 for profile 3. This is going to be the discounts for all these profiles. Now, in the second topic, I'm going to write the names of the users. So I'm going to have Daniel with profile 1. So this is going to be not with a space. So profile 1 and Ricardo, who was very helpful to help me with a blog post with profile 2, so profile number 2. So these are the profiles. Now, in orders by user, I'm going to issue 2 orders, and I'm going to take the liberty of pasting them once again. So assuming Daniel bought a MacBook Pro worth $4,000 and Ricardo getting an iPhone 11 with a particular price, now I'm going to have the payments here, the payment status of these orders. I'm going to say that Daniel paid for his order while Ricardo did not yet, or at least the system has not received the payment yet. So I'm going to have order 1 status paid and order 2 status pending. So now after I hit enter, then in the topic of paid orders, we should be getting the order ID order number 1, which is to say this one, order ID, where the amount was deducted from $4,000 with the discount applicable to profile 1 from Daniel. So the discount applicable to profile 1 is $10. So out of $4,000 minus $10, we should be getting $3,990. So let's look at the console consumer. So we have here user Daniel, products with iPhone 13, MacBook Pro 15, amount 3990.0. So this is the final price. Now the output is a little truncated, it looks a little funny. I don't know exactly why, but we got the right amount, which concludes our whirlwind of a tutorial on Kafka Streams. So there you have it, folks, a quick tutorial on Kafka Streams with an end-to-end example covering most of the important functionalities of Kafka Streams. I hope you enjoyed this video. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. Check me out on Twitter and LinkedIn with fresh updates on upcoming material, and check out the blog at rockthejvm.com and the website where I have hundreds of hours on Scala functional programming and related technologies based on the JVM. Until next time, I'm Daniel signing off.